we'll have a better idea of what date that exam will be. Okay. Um, and the final exam will be on chapters 6 and 7. So it will not be cumulative. It'll just be like, I mean, it's during the final exam time, but it's just a third exam actually. Okay, there's not much need for a cumulative exam here. The material in chapters 6 and 7 will simply just incorporate the things from the earlier chapters. Okay, so I mean, everything is just sort of building upon itself. Topics that we do later, rest on topics that we did earlier. Like lots of math courses that you take. Okay. Any questions thus far on assignment 4? I hope we've gotten started on it already. We've covered all the material necessary for problems 1 through 4. Problems 5 and 6 will cover that material today. Though I think those are more conceptual than rather than this should be easier than 1 through 4. Those problems.
I have a couple questions. First, on 1A.
1A. Yes. What about it? I'm sorry.
Oh, I was just kind of wondering how to get started.
Okay. So for number 1, so assignment 4, problem 1. All right, you got F from D to R, and A and B are subsets of the domain. So part A, prove that FA, so image of A and image of B equal to the empty set, implies A intersect B is the empty set. The best approach to this problem is not direct proof. The best approach to this is either contrapositive. Well, I think contrapositive or contradiction would be fine. All right, so this one is naturally done via contrapositive or contradiction. Okay, so for contrapositive, well, for contradiction, I think contradiction is probably the best one. I don't know. I haven't written it down, so I'm not exactly sure. So for contradiction, what you want to do is let's set up the contrapositive first. Contrapositive, right? You want to prove that A intersection B not equal to the empty set implies the image of A. Yeah, actually, this is going to be is not equal to the empty set. So, assume, first sentence, assume that A intersection B is not the empty set. So that is what? What does it mean for the intersection of two things not to be the empty set? What does it give you?
Something in both A and in B.
Yeah, that is, there is X in, excuse me, A intersection B. And then go from there. All right, contradiction. Well, for contrapositive, you do that. For contradiction, contrapositive, I think, is the way to go there. But you can do a contradiction as well. What you do is you write, by way of contradiction, right? So for contradiction, this is, image A intersect image B is empty implies A intersection B is empty. So you want to assume the hypothesis and the negation, right? Remember, P implies Q naught, right, is P and Q naught. Right? Assume the negation of that contradiction, of that implication. So by way of contradiction, assume that the image of A intersection the image of B is equal to the empty set, and A intersection B is not the empty set. Right? So there is, again, X in A intersection B, blah, blah, blah. I'll go from there. All right. I think we can do. Let's see. Right, and then for part B, the other way around is not true. A intersection B equal to the empty set does not necessarily imply that FA intersection FB is empty. And just give a counter example for that, like what we've been doing in class. Number 4, okay.
So that was going to be my other question.
Sure. So for number 4, we're also kind of doing this, this disjointness type thing, but this time we're doing it with pre-image rather than image. Any questions about what I said so far about number 1? Is that? I think that should be enough to get you started. I think if you look at it from here, you should see where to go.
Oh yeah, it looks really good.
All right. Oh, by the way, also, so comment about something from exam 1. There was one part of exam 1 that was really easy, and sometimes when things are really easy, the tendency is to over-explain, to just sort of go into all these gymnastics to try to explain it when nothing, it's not necessary. Don't overcomplicate things. If it's actually that easy, then just say it as such. It was this. It was the. I have it written down on the solutions, of course. It was this one here. Number 4 in the exam. Prove that the following statement is true for two sets A and B. If A intersection B is empty, then A intersection B complement is A. So, assume that A intersection B is the empty set. And then and then you want to show that these two sets are equal. A intersection B complement is A. So, folks, rightly thought that, okay, well, let's do, this is a subset of this, and this is a subset of that. This is a subset of A by A intersection whatever, like A intersection X is a subset of A just by definition. Right? Let X be an element of A intersection B complement. By definition, X is in A. Done. Nothing else needs to be said. That's all you need. You pick A to be an element of this first set, A intersection B complement, and then you want to show X is in A. So let X be in that intersection. By definition, X is in A and X is in the other thing. The fact that X is in the other thing is irrelevant. Okay, all you care about is that X is in A. That's it. So, I mean, I saw like people, they just kind of kept going and going and talking and saying more stuff. So this problem is like that. I mean, pretty much after what I said here, there's nothing much left to say. So don't go on and on and on. One sentence, or two sentences maybe, is all you need from here in either part. Okay? All right, number 4. Lost one. All right, it's over here. Number 4. So this is an if and only if statement. Similar to this one we just did. All right, so consider F from domain to range, and A and B subsets of the range. Okay, consider F from D to R, and A and B subsets of the range. Prove that A intersection B is the empty set if and only if preimage of A intersects preimage of B is the empty set. Right, this is an if and only if thing. So we talked a little bit about this in the last chapter, chapter 3, about proving if and only if statements. I didn't give you a homework assignment on it yet. This is the first homework assignment that has an if and only if statement. So remember, if and only if logical equivalence, that's also known as double implication. Right, so remember, P if and only if Q, well, actually I need to remember, P if and only if Q is logically equivalent to, actually I guess I need the parentheses there, P implies Q and Q implies P. So you have to prove implication both ways. P implies Q and Q implies P. So here, right, there's two things to prove, right? So you want to do the implication this way and the other way. So do this one do both of them by contrapositive, I think is the way to go here. Right, so to prove, well, I don't want you to write this. So perhaps each direction can be proven in one of 3 ways. And you don't have to do the same way for each one. Right, direct proof, contrapositive, or contradiction. Right, so I think here contrapositive and contradiction are the way to go. All right, so for this direction, right, A intersection B is empty set implies right, preimage A intersect preimage B is empty set. So here, using contrapositive, assume that this preimage A, preimage B is not the empty set. Right? So there is X in preimage A intersect preimage B, and go from there. And then for the other direction, right, you're trying to show preimage A intersection preimage B is empty, implies A intersection B is empty. So here, assume the negation of the conclusion that A intersection B is not the empty set. Go on from there. All right. Assume A intersection B is not the empty set. So there is Y in A intersection B, blah, blah, blah. Okay, it's an if and only if proof, so there's two implications that you have to show. You have to show the implication in one direction, P implies Q. So to prove P if and only if Q, you got to prove that P implies Q and Q implies P. All right, so number 4 is in contrast to number 1. For number 1, right, it's the same, it's the analogous statement using images rather than pre-images. And with images, it's just that the image of A and image of B are disjoint implies A and B are disjoint. The other way around doesn't work. A intersection B being disjoint does not mean that the image of A and the image of B are disjoint. But pre-image, as usual, behaves more nicely. Behaves more nicely than image. Okay. Anything else? About this assignment? So far? All right. So going back to our lecture here on chapter 4, we left off last time with the following problem. So given a function f from domain to range and a subset of the range, we want to prove that the image of the pre-image of A is contained in A, and we proved that. And it's pretty much straight by definition. So the image of the pre-image of A is a subset of A. By the way, this is not function composition. We haven't talked about function composition yet. Okay, we have not talked about it yet. This is not function composition. This is images and pre-images. I mean, of course, it's pretty much, doing the image of a pre-image is a lot like function composition, but it isn't exactly that. And then show that A is not necessarily a subset of the image of the pre-image of A. I thought... Oh, yeah, now we were doing the other way around. Yeah, so we gave a counterexample to that. A is not necessarily a subset of the image of the pre-image of A. We gave, so here's an example of domain and range. A is R comma S, right? So R and S are not in the image of the function, F. So the preimage of A is empty, so the image of the preimage of A is the empty set. So in this example, A is not a subset of the empty set, of course. Another example, given F from D to R, and A is a subset of the domain D, prove that A is a subset of the preimage of the image of A. So one sentence proof, two sentence proof. And now we need a counterexample for the other way around, that the preimage of the image of A is not a subset of A, necessarily. Not necessarily a subset of A. Anyone see an example? Right? What's the malfunction that can happen? Basically, the preimage of the image of A, it's going to be bigger than A, right? We know that A is a subset of the preimage of the image of A. The thing is it can be a proper subset. It gets bigger. The preimage of the image of A is more than A, typically. Why? What happens? What can happen that makes the preimage of the image of A bigger than A? So like here's the domain. Put 6 things here. 1, 2, I don't need 6, just 4 things. 1, 2, 3, 4. And here's the range. I'll just put 1 thing in the range. Or 2 things in the range, A and B. Or X and Y. Right? What's the malfunction that can happen that makes the preimage of the image of A bigger than A itself? Say this is A. So they both go to X. Right? In this case, the image of the preimage of A is what? So A is 1, 2. Right? So the image of A is what? What's the image of A? It's just X. Come on. It's just X. So the preimage of the image, of the image of A is going to be what? So what's the preimage of X?
1, 2.
1 and 2. So they're the same in this case. So it's not bad. What would make it? This is not a counterexample, right? I mean, in this case, A is equal to the preimage of the image of A. So it is a subset, right? What can I do to mess it up? What can I do to mess it up? What can I do to increase this? To make this bigger than just 1, 2?
Make A bigger.
That would work. I was just thinking just to send 3 to X as well. Right? And so A is 1, 2 in this picture here, and F in the image of A is just X. But now the image of the pre-image of A is what? Right? The image of A is X. So the image of the pre-image of A is the pre-image of X. But what's the pre-image of X in this case? In this picture here.
1, 2, and 3.
1, 2, and 3. Right, which is not a subset of X. Right, A is 1, 2. Image of A is just X. So the pre-image of the image of A is 1, 2, 3, because 1, 2, and 3 go to X, and that's not a subset of X. Okay. So there you go. This is another, illustration, not another illustration. This is an illustration essentially showing that inverse functions don't necessarily exist. All right, because if inverse functions existed, you would think that the image of the pre-image of A is equal to A. It doesn't have to be. Or that the pre-image of the image of A in the domain, for A in the domain, is equal to A. Doesn't have to be. Not for functions in general. Okay, it's only very special functions that have inverse functions. Images and pre-images always exist. Inverse functions don't. When they do exist, these two things are going to be equal. So let's talk about that, finally, at long last. Start on this. Okay. Definition. A function f from D to R, domain range, is called injective. Okay, or 1, 2, 1. So injective is kind of the more fancy name. 1 to 1 is the more sort of colloquial name, although it doesn't matter. You can use either or. So a function f is injective, or 1 to 1, when, okay, for every A and B in the domain, A not equal to B implies f of A not equal to f of B. Different elements in the domain go to different elements in the range. You don't have this. So, for example, so here's a function. 1, 2, 3, 4, 5. W, X, Y, Z, P, Q. So this function here is 1 to 1. This function here is 1 to 1 because every element, different elements in the domain go to different elements in the range. 1 and 2 go to W and Y. 2 and 3 go to X and Y. 1 and 5 go to W and Q. So on and so forth. Right? Every range element has at most one in arrow. Right? Every domain element has one out arrow. That's the definition of a function. Every domain element has one out arrow. But in the range, you can have several elements. You can have an element having several in arrows, and most of the examples we've looked at thus far do that. But with one-to-one functions, every element in the range has, at most, as either 0 in arrows or 1 in arrow. So that is one-to-one, and this is not one-to-one. Oops. So not one-to-one. Not one-to-one. We have that 3 is not, or 2 is not equal to 5, but f of 2 is equal to f of 5. Right? F of 2 is equal to f of 5. They're both equal to y. Okay, but 2 is not 5. So one-to-one means when domain elements are unequal, the assigned range elements are unequal. Or equivalently, by contrapositive, image A, not image A, f of A equal to f of B implies A is equal to B. Right, so A not equal to B implies f of A not equal to f of B, or f of A equal to f of B implies A is equal to B. This is the contrapositive of that, which of course is logically equivalent. So in this picture we have example. Another example. One. F of x equal to x squared, right, defines a function f from the set of reals to the set of reals, right, like calculus type function, algebraically defined function. Is it one-to-one? Is or is not one-to-one? Do distinct domain elements go to distinct range elements? Or is there a range element that comes from two distinct domain elements? Is this function one-to-one?
Yes.
Yes? Does x not equal to y imply fx not equal, imply the function x squared not equal to y squared? Is that true?
It's not one-to-one.
It's not. For example, what's the counterexample? Or a counterexample?
For example, like 2 squared or negative 2 squared.
Yeah, exactly. 2 and negative 2. So it is not one-to-one. Right? For example, right? For counterexample, right? It's not that distinct elements in the domain have to go to the same elements in the range, right? I mean, like, 1 is not equal to 2, and 1 squared is not equal to 2 squared, right? 1 is not 2, and neither is 1 equal to 4, right? But there are elements in the domain that are not equal. there are elements in the domain here, like 2 and 5 are not equal, and they both go to the same range element. For example, 2 is not equal to -2, but f of 2 is equal to 4. May not write the 2, but 2 squared is equal to -2 squared. And so not 1-to-1. How about this? Another calculus type function. So f of x equal to 3x minus 2 over x minus 1 defines a function f from the real numbers except 1 to the real numbers. Is this function 1-to-1? Is 1-to-1. Here's a proof. Okay, so when you want to show something is 1-to-1, typically the contrapositive statement is what you want to prove, right? Assume that f of a is equal to f of b. Show that a is equal to b. And that's typically the way you want to go. To show something is not 1-to-1, you want to go with this. Take, find an a not equal to b where f of a is equal to f of b. Right? Something where this is true, but this is false. So here's a proof. Okay, we will use by contrapositive. All right, that is, assume f of a equals f of b, right, and then show that a is equal to b. Assume f of a is equal to f of b, and then show that a is equal to b. All right, so this is the function here. So assume f of a is equal to f of b. That is 3a minus 2 over a minus 1 is equal to 3b minus 2 over b minus 1. What can we do from here? Very little words in this proof. This proof is mostly just a calculation.
Cross multiply.
Cross multiply. So we get 3a minus 2 times b minus 1 is equal to 3b minus 2 times a minus 1. So notice I am not working in a chain. I'm stacking my equations. Stacking equations is when you're solving an equation. And that's what we're doing here. We have this equation for a and b, and we're kind of solving not really finding, you can't find the values for a and b. What we're doing is showing that we're looking for the solution that a and b are the same. That's the solution we're after. So 3ab minus 2b minus 3a plus 2 is equal to 3ab minus 2a minus 3b plus 2. 3ab's, they cancel. Plus 2's, they cancel. So I'm left with minus 2b minus 3a is equal to minus 2a minus 3b. Move the a's to one side, the b's to the other. All right, so this gives me 3b minus 2b is equal to 3a minus 2a. So b is equal to a. as required. Period. Right? We assumed that f of a was equal to f of b. We assumed that f of a is equal to f of b. And now we have that a is equal to b. B is equal to a. Whatever. Right, and it was just done through a calculation. Fa equal to f of b. That is, right, the function is 3x minus 2 over x minus 1. So f of a is 3a minus 2 over a minus 1. F of b is 3b minus 2 over b minus 1. Then we do a bunch of, bunch of algebra, and we found out that a was equal to b. Okay, so showing a function is not one-to-one. You have to find distinct elements whose images are the same. To show a function is one-to-one, take two elements whose images are the same, and show that those elements were the same to begin with. Must be the same to begin with. So on assignment 4 here, here's a function f from z cross z to z, given by f of the pair xy is equal to x plus y. Draw the image of the inverse image of, or the pre-image of 1, 2, 3, and 4 on a standard xy plane. That'll have a nice geometric description, as you will see. Show that f is surjective. We didn't define surjective yet. Show that f is not injective. In other words, find two elements x, y, in z cross z that are different. So x, y not equal to a, b, but x plus y is equal to a plus b. So this function is not injective. Okay. Surjective. A function f from domain to range is surjective, okay, or onto. So the word onto is a little bit as an adjective. It's used as an adjective here, which is a little bit awkward. So surjective is kind of the term that's more often used, with injective and one-to-one. Those are interchangeable. But the word onto is really kind of awkward. So surjective is really the one that gets used more often. So a function is surjective when the image of the function is the entirety of the range. Nothing in the range is missed. Right? That is, in other words, for every y in R, there is x in R, or in the domain, such that y is equal to f of x. Everything in the range gets hit by something in the domain. And a lot of the examples we've been looking at, I've always left out, certain range elements from the image of the function. Right? Here I left out the p. Here p and q both got left out. A function is surjective when nothing gets left out. So let's just copy this over and fix the range. For example, so if I get rid of those, oops. this function is surjective. And then if I just leave the example the way it was from the last one, is not. Right? Everything in the range comes from something in the domain. Here, there are things in the range that don't get hit by domain elements. Okay, so that is every range element has an in arrow. This one is not surjective. Some range elements have no in arrows. Exercises to think about. Oh, let's do some more examples before we get to that. So again, consider the function f from R to R given by f of x equal to x squared. Is this surjective? Does every element in the range get hit by something in the domain? So f of x equal to x squared is the classic example of a function that is neither injective nor surjective. Right? How is it not surjective? What range elements are missed?
Would just every y value on an xy plane be considered part of the range?
Not everyone, just the, which ones? Yeah, think of the graph, right? I mean, think of the graph of f of x equal to x squared. All right, that's, in calculus, in calculus, the range of a function is the stuff that is really the image of the function. Unfortunately, terms don't always get used the same way. So, and when you're talking about calculus, in calculus, when they say range, they mean just the elements that are hit by domain elements under that function. Okay, but here, I mean, I'm saying the range is all real numbers. Okay, here the range is simply specified. All right. So which range elements are missed? And that's more the standard formal definition. You have a function f from domain to range. Every element in the domain goes to something in the range.
The negatives.
The negatives, exactly. Yeah. I apologize for that. 400 years of calculus pedagogy is just not. Mathematical pedagogy has just not come up with standard terminologies for things. It's just. If any of you become professional mathematicians, if you go into my subfield of mathematics, combinatorics, the nomenclature is so not standardized. It's comical. I mean, things have like 5 different terms that people use to describe them, depending on what context or what country you're in. So a range of a function is just something that's given. Okay, it's not automatically surjective. In calculus, things are automatically surjective. But then again, if they're automatically surjective, then you got to figure out what the range is supposed to be. All right, but here, anyway, this is not surjective. No. -1 is an element of the rails, right? And -1 is not equal to x squared for any x in the rails, right? So that range element gets missed, right? So here the image of f is actually equal to what? It's actually equal to the interval from 0 to plus infinity, right? It's just the positive reals. So if I was to do that as a second example, thank you for bringing that up. So consider f from the reals to the positive real. So you can say this in set notation, set builder notation. It's a set of all x such that x is bigger than or equal to 0, which is often denoted, well, we'll just leave it at that. So let's look at a function f from the reals to plus infinity, defined by f of x equal to x squared. Is f surjective? Yes. All right. Here's a proof. All right. Take y, an element of, all right, the interval from 0 to plus infinity. All right, and then let which domain element goes to that range element. So you take y is bigger than or equal to 0. Which domain element, when you square it, goes to y?
X.
Which x goes to y? Which x, when you square it, is equal to y?
Square root of y?
Yeah, square root of y. Let x equal to the square root of y, and so f of x is square root of y squared is equal to y. Period. So we picked y from 0 to plus infinity. We picked an element y from 0 to plus infinity. And then we found an x, which depends on y, an x written in terms of y, such that f of x, when you square it, such that f of x, when you plug x into that function, gives you the y that you started with. But the x is going to have to be expressed in terms of y. Look at the definition one more time. For every y, there is an x. Right? For every y, there exists an x such that blah, blah. Well, not blah, blah. F of x is equal to y. For every y, there is an x. Now, whenever you say for every y, there is an x, that x depends on the y. The x depends on the y. Right? Every student has a name. The name depends on the student. Right? Your name is Mark. Your name is Sally. You know, whatever the case might be. You know, that name depends on the student. When you say there exists an x for every y, that x is universal for every y, right? There is a name that every student has. That name is Raider. Every student at Wright State has. So in this example, the x that you pick has to depend on y. So y is an element from 0 to plus infinity. So you pick x equal to the square root of y, and now when you square the square root of y, you get y. So third example, let's go back to this example over here. So f of x, it defines a function oh, 116. From this to, well, there's one thing I got to leave out, 3. Well, we'll talk about this next time. We gotta go.